Cool. Okay. I'm going to start here. So we have finished. We have finished differential calculus. We finished half of calculus. We're going to do the other half now. And that's funny, derivative calculus or differential calculus, the opposite of that is antiderivative calculus. All right. Or something called integral calculus. But here's what we got. We've done this right here. We went from position, right, we looked at the slope and we looked at concavity. If you think about it in terms of physics, what we did was we went from position, went to velocity, and went to acceleration. Right? The derivative, second derivative is acceleration. What we want to do now is go the exact opposite way. So guess what? All those rules that we learned, no, we got to go exactly opposite of those rules. Okay, so let me give it to you here. Right? What's the derivative of sine? Cosine. What is the antiderivative of cosine? Back to sine. We're good. So everything flows the other way on this. So let's get ourselves a definition, and we go. And then one thing we have to think about, which is a tricky part, but we'll talk about it. Let's go with it first here. Definition: a function capital F. We're going to call that the antiderivative. We're good. So whenever you see a capital F, normally in calculus, bless you, that is the antiderivative of F. Of course, has to be on some kind of interval, whatever it is, right? And if we define that to be, that means that the derivative of the antiderivative is the function itself. We good? So then if f, the antiderivative, the derivative and the antiderivative is the function for all sets in the interval I. Sorry, proper definition, got to give it to you. And then we're going to come up with a little problem that comes up in calculus. Here's your antiderivatives. It's like, what? But why? Okay, are we good to go? Jamming. So can you guys do this for me here? Can you guys find the derivative? Let's go back just real quick here. Find the derivative of these two functions, and we'll kind of give you that one. Can't give the answers yet. The derivative of that function. Awesome. And then the derivative of this function. So there's 2x squared plus 10, obviously, yeah. Derivative of 2x. And the derivative of x squared plus 15. Answer is? Oh, we got ourselves a problem. We have two things. Notice the two things, they're different functions, aren't they? But when you take the derivative, we're going to actually have the same derivative. But, you guys talk to me, see if you guys agree. The derivative, the functions themselves only differ by a constant. True. Right, if this had an x next to it, this would then be 2x plus 15, right? It's the constant, that's the problem. Okay, so let's do this here. Two more, real quick here. Two more. Derivative of this guy? 2x. And then the derivative of this guy. Ah, gotcha. Okay, so trying to get somewhere, good? Trying to get somewhere. So if it was a variable, we don't care about the variable. Yeah, there you go. You are. Okay, so here's what we need to do. And once we get that, then we can go on from there. So I want to just do a graph. I'm going to move it ahead real quick here. So let's go back to this one right here. So x squared, if we're to graph x squared, you guys know how to graph x squared? Go for it. Can you guys do that? And then can you graph, I'm going to go back. Can you graph x squared plus 10? Then can you graph x squared plus 15? So A, B, and C. I want you guys to graph A, B, and C. A, B, and C, not the one that gave us 2x plus 1, not that one.
What? Way less than 4 months. Really? You're like yes. You're like a little over a month of after school. Oh my.
Like one of his vacation, yeah.
X squared plus 10 is.
So I got x squared, is that right? I have not x squared plus 10 would be like right here, is that right? X squared plus 15 would be another one. I didn't draw it out, but you guys okay with another one right here? Like this?
I'm doing this on Duolingo, so just like think about how like expensive it is. How expensive? Yeah. Okay.
All right, we'll let Noah order rice real quick here.
I can't remember if Gohan or Gohan. Yeah. That's your answer from Dragon Ball. Gohan. I know like witty and small amount of knowledge.
All right.
There's like that's true. I got like 20 words that I recognize.
Okay, you guys are okay. If I would put a negative in here, we got this right here, right? So notice the derivative of 2x gives us all these different functions. So we say this, the derivative, if, real quick, so mind switch, you guys ready? If f of x was the original function, right? If 2x was the original function, then the antiderivative would look like, and then what's the letter we'd use for constant? Ayo, that's cool. How about a C? So it's going to be x squared plus c because it could be any one of these functions. We're good? So all of those would give us a derivative of 2x. That's what we got to kind of keep in mind. When we take the antiderivative, we possibly go into multiple values that have derivative because of the constant rule. So again, a theorem. You guys ready for this? Writing this down? Again, that's the concept. We're good? Right there. And then we'll do some problems. That makes sense. So if you guys want to write this down, this is the theorem. So if f is the antiderivative, right, of f on an interval, then we write the most general antiderivative possible, which is f of x plus c. C is an arbitrary constant. How did I do this? No, you guys write that down?
Analog class, analog attendance. That's crazy. That's just rice.
All right, are we good? So, okay, just this concept of the antiderivative gives us multiple answers.
Dean walked out. Dean walked out. Oh, shit. Now he's building a wall. Joe's kind of like these kids like Reginald, right? That's like one joke. First son, Joe. So it's Joseph. Fourth son, Billy. Fourth son, something that don't like him. What if you have a bell Joseph? As soon as he saw him, like, no. Are you kidding me? What is the girl? You should still like Joe.
All right, perfect. Okay, so we're gonna start off simple. We're gonna get more complicated as we go. So let's go with it. Got a few problems to do, and we're gonna get more and more complicated here. Again, we're undoing the derivative, right? So think of that as a derivative. The antiderivative would be what? And if you think about it, you gotta, here's how we think about it. Sine goes to cosine, and then cosine goes to negative sine as a derivative, right? And negative sine goes to negative cosine, and then it just keeps on going, right? So if we are at sine, it's going to circle back to the top. Oh, cool, cool. So we just write capital F. We're going to get there. For now, we're just going to use capital F because we're going to get there in a bit.
So normally the derivative of sine of x cosine, right? Normally the derivative of sine of x is cosine x. And then so how do we get negative cosine?
Yeah, so if you repeat this, right? Sine goes to cosine goes to negative sine goes to negative cosine, the negative cosine goes to sine, and then we go back up the list, right?
Because so you can think about like
what goes
up?
up?
What's derivative is sine?
Yeah, if you took the derivative of that, yeah, what would give you sine? Yeah. And then eventually you'll learn like, oh yeah, that's antiderivative. You eventually, like just like you guys did radian measurement, you convert back to degrees for a while, but then eventually, yeah, I know radian measurement. Okay. Oh, sorry. Guys, we're missing one piece over here. This is wrong as of right now. Plus C, right? We have to always think about this constant that's added to it. Okay, are we good there? Yeah, we're good there. Cool. All right, next one. Of course, this starts off simple, gets a little more complicated. Here we go. Oh, that would be too easy. Derivative of, antiderivative of cosine. Sine, right? It's this little piece right here, and then moving back up the list. So at first, Hakan had a good point here. Do you guys remember in trigonometry when I introduced radian measurement? You're like, I hate radian measurement because, and then I converted everything to degrees for a while. Then eventually you just learn radian measurement, right? Same thing's going to happen here. You're going to confuse derivatives, antiderivatives for a while. And then eventually you're like, oh, that's just antiderivative. Let me go this way. And it just becomes second nature. But the antiderivative of cosine is sine plus c. Perfect. Okay. Okay. So here's what I want to do. Okay.
I don't know. Like, everywhere I go, it's not like I'm smelling it. It's just like when I was like, I'm not usually like casually in my hair and smoke.
So what you guys do on the reference page is, like for these ones here, for A, right? For A, you're looking at number, where's sine? Sine goes to, oh, you don't see. It's kind of like 13, right? But you got to think about it in terms of, so let's see. So A, there is no reference here, right? For B, there is a reference, cosine. Cosine is number 13. So this is number 13 on our sheet. Everybody okay there? That's number 13 on our sheet. And you're just going backwards. You're going from cosine back to sine. Okay, so let's take a look at just the trig functions here. So number 13, you guys are good? Sine goes to cosine. 14, cosine goes to negative sine. That's cool. 15, tangent goes to secant squared. Okay. 16 is secant goes to that. 17, oh sorry, cosecant, yeah. Secant number 17 goes to that. And then we have 18, which is cotangent goes to that. So tell me this right here. Of course. Let's start with a weird one here first. This one. Do you guys see the end? Do you guys see the derivative that says tangent? So we can go back to the antiderivative. That's the, yeah. So notice there is nothing that says tangent. So as of right now, we do not know the antiderivative of tangent. So guess what we put down? We don't know. Yet. Yet. There's a little yet there. Okay, next one. How about this one? Do you guys see a sheet that says secant squared? Yeah, answer is tangent. Okay, so plus c. Perfect. So we're using the derivative sheet to give us the antiderivative. And that guy. Okay, so next. So then let's think about the power rule now. The power rule for derivatives is you multiply the number in front, is that right? And you subtract 1 from the exponent, is that right? Power rule, where's that power rule? Do we have the power rule in our sheets? Yeah, number 8, okay? So here it is. Can you guys give me the antiderivative of that? So for the derivative, oh, good. So we have to add 1 to the exponent, is that right? Now we add 1 to the exponent, and then we divide by 2. We good there? So instead of multiplying by the exponent, subtracting 1, we notice that even the process is reversed, right? We do the exponent first, and then we do the divide symbol later. So if you were to write this down, that's the derivative. So the antiderivative does this. We add 1 to the exponent, and then we divide by the 2. So the power rule for antiderivative, as long as this, what's the only time this cannot work? A -1 would not work. Is that right, guys? Check this out. If it was a -1, -1 plus 1 would give you a 0. Good. So there's a little condition here. Okay, you guys good? All right, we're good. Question? No, okay. You guys go with F. Here we go. Let's work a little bit on the. Let's work a bit on the power rule. Answer here is. So give me the antiderivative for now. Then you can be a computer scientist. No, it's not x squared plus c. No. No. It is something. Anybody? Give me. I go with that. So we are going to add 1 to the exponent, right? And then divide by that exponent, right? So plus c. Are we good? Joe, we good with x squared plus c? Everybody okay with x squared plus c, right? We add 1 to the exponent. We divide by that exponent. Next one. That one would be? Oh, I know.
X to the 5th
Perfecto. We good there. X to the fifth over 5 plus C. Don't forget the C. Okay, and last one. How about a generic one? Let's actually create the generic formula. This is going to be x to the n. So if that is the case, what's the antiderivative going to be? So over n plus 1. Perfect. Okay, when does it not work? When n equals -1. How come, Joe? Yes, so the only time it doesn't work if n is equal to -1, because -1 plus 1 is 0, and then you can't divide by 0. That's the only time it does not work. Shucks. So guess what the next problem is? Anyway, it doesn't work, yeah, because, oh, I did explain it right here. Yeah, x to the 0 is still fine, because it's 1 over, so if you just had 0 like this, that would still be fine. But then the -1 is the problem, because then you're going to divide by 0. That doesn't work. So -1 doesn't work. Okay, so then the next problem is find me the antiderivative of x to the -1. Oh, cool. Okay. Any? Let's see. Let's see what you do. Let me catch others. So on your derivative sheet, guys, find me 1 over x as the end of the derivative process. And tell me what number it is. See again? Number 11. Yes, 11 is the answer. I heard you. Okay, so according to the derivative sheet, remember the derivative of ln is 1 over x, right? ln of x. So the antiderivative is this one. The only thing we have to be careful of on this, guys, is the fact that ln does have to be, right? ln doesn't work in negative numbers. So it has to be this. And then also, you know that it can't be 0 either, right? It has to be greater than 1. So there's some conditions that are set in here. Okay, got that one done. Okay, how about this one? I know this one from previously. If you want to, you can put that as well. The antiderivative e to the x. There it is. Plus c. Okay. E to the x plus c. E to the x is its own derivative. Okay, got that one, that one. And oh yeah, there's a K. I'd go with that. For sure, for sure? Is this your final answer?
No. We have the H in front or something.
So on your sheet, hyperbolic sign. What's the negative? Yes.
Negative.
No, it's actually just cost, not negative.
Oh, okay. I don't know.
It would be negative cost.
It'd be negative.
So remember okay, so let's go. This is number 25 and 26, right? So the derivative of sinh is cosh, and the derivative of cosh is sinh. So a negative is just going to be hanging there on the outside, right? But look at number 25 and 26. Uh-huh. Yeah, so
Think about how many she's paid off. Think about how many she's thrown away. 30,000. Literally thousands. She better make it good.
dang, that is a requirement. It should be just like lessening, like, oh, you're almost there. So you figure what? About 180.
Wait, no! Oh, this is beautiful the way it's beautiful.
So let's do this here. Oh, wow. Okay. So for the regular sine and cosine, this is the pattern, right? For the sinh and cosh, this is the pattern, right? Pattern is just this to this, this to this, right? They're always positive. There's never a time it's negative. And if there is a negative, yeah, we can stick it out in front. Constants can still stay in front. Okay. Next, how about this one? I got an L. That. Negative cosh plus C.
Negative sine.
That would be something to the negative 1/2. Oh, it's
Oh,
cosh
inverse
inverse.
x.
That's awesome.
Good, good. So if you look at the one that fits, it has to be a square root. It's number 32. Ever see number 32? Number 32. It's cosh inverse. It's that one right there plus C. I know, we did it for like 2 days, and that was kind of it. That was a quick one. Okay, got that one. Next is H. So this was number 32 if you want to label it, right? So go back, just so you know. So technically, we have the power rule in our hands that we do it mechanically, right? The other ones we are looking at the sheet, right? Yes.
No, you guys have like
Okay, and the next one.
like summer or something. Dude, he's gonna be at the most important job interview of his life, and he's just gonna come through the door. That's a fight.
Where's that?
You're like standing, and then just like,
Oh, yeah.
whoa.
Okay.
That was
Is this one sine H inverse?
No.
Because it does. Oh, no, it's not.
Nope. Waiting for that one.
No.
Let me check something. Tan inverse. Are we doing tan inverse? Right. It is. What number it is? What number? What number?
27.
27. Hey guys, take a look at this here. Take a look at number. No, it's not 27. 21. Okay. 21. It's number 21. Hey guys, take a look at this one. 21 and 24. Notice the difference between tangent inverse and cotangent is just a negative. Then jump down to number 33 and 36. 33, 36. What do you notice there? They're the same. Weird. Okay, so then those will get us stuck. Okay, so we got ourselves, so that's tangent inverse, right? According to the formula sheet. There it is. Okay, and yeah, we can get an N. No.
Oh, no. Oh, yeah.
Okay, think. And let's go with N. Okay. So here it is. Now we get into funness, putting them all together now. Before we take the n term derivative, let's simplify as much as we can. How about that? That guy I don't like. Whoa, that's, guys, this is crazy. That would be a quotient rule, is it? Like, how do you undo a quotient rule? I have no rules for that. But I think I can do this. Can I separate the x? Can I separate the x into two different pieces?
Oh,
So eventually we probably could figure out how to do a quotient rule, maybe, right? But for now, we just have no rules for it. Good? Yeah, let's go with, so that would be 2x, Luke says, to the fourth, because 5 minus 1. Okay, that's cool. And then what is this one going to be? Minus, oh, I'll go with that, yeah. So that one's going to be technically this over 1, and 1/2 minus 1 is a negative 1/2. So we got ourselves an x to the negative 1/2. You could write it like this on the bottom. That's fine and dandy, but we don't like to write it like that because it doesn't help us with the power rule. Is that right? So then we write it like this, negative 1/2. Everybody okay with negative 1/2? Okay, your job is now to take the I think we're ready. Take the antiderivative of this guy, and then of course you're gonna have to simplify. Negative okay, plus 2x to the fifth over 5. Over 1/2. Okay, cool. Joe, what do we do here? Up as a 2 over here. Awesome. Don't forget the plus c. Oh, that's cool. That's cool. Hawkins think actually really correct about this here. So each one of these, because we're doing them individually, right? There should be like a C, like a C1, C2, C3, but because all of them are going to be constant anyways, eventually it's still just going to be a constant for the whole thing. But yes, that is actually a really thoughtful way of seeing it. There's calculus books that explain and prove the fact that you can actually combine it into one C value. There are calculus books that make you do C1, C2, C3, and then at the end you say C is equal to C1, C2, C3. Okay, final answer right there. We good? Okay, and this one, let's go with this one here. Okay, some extra directions here. Here's what I got. I have find. So notice I'm not using a uppercase letter for the inverse. So find the original function. Find the original function. So this is f, right? If the derivative is already e to the x plus. And then we also know that f of 0, the original function, if you plug in a 0, will give you a negative 2. Yeah, cool. So then somehow we'll solve for the c value. All right, I'm gonna let you guys try yourself. Go for it. If you have enough information for you guys to try. So, how did you undo the derivative? So, yeah, you keep the 20 out front. Constants can stay out in front, right? Just as derivatives can. Oh, we don't have no chain rule rules either, right? Shucks. It's 1 plus x squared to the negative 1, right? Oh, chain rule means that there's chain rule just means there's functions inside other functions, right? So that's a function 1 plus x squared, but it's inside the function of negative 1. Right? So it's a function here and a function here. Oh, remember you can't just add the exponent, right? Because it goes zero.
Well, I'm gonna throw a little DNA. I'm playing 10. No problem. Was there 20x at some point? Is there 20 there? Is there 20x originally?
So,
no.
all because I would assume a product would
Hear me out. E to the x.
E to the x, that's good.
Okay. Plus
E to the x is a good one.
27. We can use the fact that f of 0 equals -2. So if we put 0 in for e to the x, that's just 1. So the rest of it has to be.
Hold on, though.
The rest of it has to be -3.
Notice it's not a derivative. It's not f derivative of 0 is equal to -2. It's the function itself is equal to
Right, but if we reverse it, we can still e to the x.
Right, but you have to have the whole entire original function, right?
I know, but I'm saying, but if you plug in 0 for e to the x, you get
Yeah,
a
because you
1.
plug into a derivative.
So the rest of it should be -3.
How come -3?
Because 1 minus 3 is a -2.
Oh, 1.
Because if you put up it, because
Yeah.
if we reverse it to, we're still going to have e to the x, and you plug in 0 for x, then you get 1.
That is a very thoughtful.
So then you have the rest of it has to be equal to -3. So can we just?
So you know your c value is -3. That's cool. Now we need to figure out is what's the 21 plus x squared to the -1 thing?
I think that bit
in the
is-
original function.
20 times 1.
That should equal.
But what is the function itself? That's what. So the c. Well, by finding -3, you guys just found the c value, right? C value is -3. Got that? That's cool. And I know that piece there. Actually, no. So the middle piece is not equal to -3. Just -3 is the c value.
I think that piece is negative.
20 times 1 plus x squared minus 1 times
Interesting.
Or like the reverse of that.
Yeah,
The antiderivative of that.
Yeah. What's the integral of that? Should I tell you? We have already done it before. How about that?
Oh, wait. Is it which is 1 over 1 plus x squared? Is tangent inverse?
I go with tangent inverse. Anybody?
Wait, how?
How's the tangent inverse?
Yeah,
Anybody?
how's the tangent inverse?
So
So
1 plus x squared to the negative first power is 1 over 1 plus x squared.
So let's see. Let's make
So
sure.
the constants just stay the same.
So that's the derivative. This is the derivative. There. So let's see if this makes sense. Yeah. So Luke says -1 is the power, right? That's going to be the reciprocal of this. So reciprocal of this guy is 1 over 1 plus x squared. Good there. So Emma, you came in. I don't think you've seen this one before. So we're trying to find the antiderivative of this. So we write this differently. We were stuck for a while. And so that -1 right here, it's kind of stuck. Notice that there's a function inside, a function outside now. So we're stuck on this one until we make it into this, because the reciprocal of this is this. And then we can start the antiderivative process. So notice that constants just stay constants, right? There's no need to do that. So e to the x, antiderivative e to the x is e to the x plus 20, and then there it is. This guy, what number is this on the sheet? 21. Number 21 gives us tangent inverse, and we need to put a little plus c over here. Now the only thing we do know that f of 0 is equal to -2. Oh, Hawkins. So the reason why I said that this part cannot or does not have to be -3 is because we don't know the value of this as we get into the antiderivative. Does that make sense? But this one still does not have to be -3. Only if this is 0. Yeah, only if this is 0, then the constant will be -3 because it's going to be a value here.
But 20 tangent inverse x plus c.
Yeah, just I think because tangent inverse is 0. That's why. This part's going to turn into 0 for us. If this turned out to be a 10, right? Then this would have been 11. This would have been a -14 or something like that, right? So now we plug in. We know the condition, initial condition is f of 0 is equal to -2. So we say -2 is equal to, that is a 0, that is a 0, and then we need to figure out what c is, if that's the case. So guys, we have entered into the other side of calculus.
So just one,
Yeah,
yeah,
one.
one tangent inverse.
It doesn't take that much
zero.
time.
So it's just
Okay.
1 plus 0 plus c.
Oh, we have to graph it.
So c equals -4.
So tangent inverse, when is tangent 0 along the unit circle? It is 0 at right here, is that right? It's when the y value is 0 and the x value is 1. Therefore, it is right here at 0.
Oh, look at this interesting workflow. There's some jam right here. Dude, of course I'm on a debate team. I don't know who the frick it was. It was like fraudulent. I had no idea what that meant. It was like the most goated use of that word in the sentence ever. I was like, holy, there's a problem.
Okay, are we good there?
Yeah, that's what I'm saying.
Final answer?
Yeah, wait, no.
Tell me if you guys agree with final answer.
Fraudulent?
No, low key. It's like when you say you stand for something, but you actually don't. So it's like fraud. Like, how do you feel? It is kind of your enemy, your nemesis, your fake nemesis. That's the fact that yeah, just like the final one.
All right, let's go on to the next one. Let's see. So that's first derivative.
No, with the lunch.
No. Moldy sandwiches.
But Joe eats it because he won't make his own.
Everything gets free though. Dude, I'm not gonna lie.
He doesn't get every Friday.
Dude, you can get a meal 10%. You realize that, right? They give you 3 meals a day. Oh, yeah. All right. Dude, you know what I'm gonna have? I'm gonna have to. My grandparents are so down about it. Everything to make sure I'm okay.
You're gonna
No,
also.
you don't want the fact subscription. You don't factor.
You're gonna go. You're gonna.
I'm gonna say, already has the fact.
Yeah. You're gonna go to McDonald's like every day.
Yeah. You know they talk about like putting on freshman 15 and pounds. Those are I'm gonna show up 1 with 300 pounds of pure unlimited muscle.
Nope. I'll take this, eh? Yeah,
No.
eating the muscle of an animal does not count as gaining muscle mass.
Dude, but like I think
A cow and you
so
eat
easily.
the whole
I
cow.
yours. I think you put it here. I would be. If that was true. I would be. Last time I saw you eat, we went, we got froyo. Those froyo was more than the other two combined. Then we went to Woodstock, you got a piece of pizza. Then you went to Blackhorse, got chocolate milk and cookies. Dude, yeah. No, me and Kelly and Noah were on a call making a debate questions. Oh, yeah. And Noah started off eating like this chicken and rice bowl from Costco. His camera set up, he was lounging on the couch with it right here. And then he like went to the fridge, put his phone in the fridge, like poured a huge glass of milk, and then was like eating like chips and queso.
Oh, don't tell me about queso.
No, here's the best part of it. The queso was expired. Oh! It was like juice. It was like liquid. Like, he poured it out and it was just liquid on his face. But I still finished it. No, that is rank. That is rank.
All right, guys, we got one more or two more. Maybe.
One more, please.
We got second derivative. I know to be 2 minus x 12x.
Oh, no.
So that's all I know. It's the second derivative. I want to get back to my original function. And I know that f of 0 is equal to 1. Okay. Thank you. First derivative is what? 2x minus, let's see, was it 12x squared over 2? Oh, plus c, don't forget that little guy, right? So eventually 2x minus 6x squared plus c. Okay, but hold on. We've got a c value here. We don't even know what that is, right? Okay, so that was the, sorry guys, real quick, go back. So this is the first derivative, is that right? Okay, and then the original function. So what happens to the c? What happens to c when we take the antiderivative of this guy? It stays there. So, oh, cool. So if you move up one notch, right, a constant has a what next? An x, right? Yeah, because whenever it had like 4x, right, derivative of 4x would be just 4, right? Derivative of negative 12x would just be negative 12. So if this is the case, we finally got this right here. We got this guy to be, let me go back and forth, just make sure. Let me write it over just so we can see it here. So this over this, right? Minus 6, x to the third over 3. Plus, now we've got a cx. Oh, hold on, we got to distinguish because I can't put another c here because that means these guys are both the same. So, yeah, twice because we were started at the second derivative. So I got to label this as something different. So how about c1? We good? So this will be c, this will be c1. They'll get to c4. That's a little different. Okay, so.
I think you divide by 3.
Okay, yeah, so then just to simplify it, here's my simplified, simplified form is x squared minus 2, right? Right there. Okay, here's what we know. Don't take off your shirt.
He's like, I tried twice. Two. No, it's just divided Dude, I can't afford that like that. You haven't got enough
All right, help me out here. Help me in more ways than one over here. Okay, so we plug in. Okay, so if I plug in this one right here, right, that means I have a 9 is equal to, let's 0 plugged into here. That's 0. That's 0. Oh, nice. Okay, are we okay with C1 being 9? So that's a 0, that's a 0. I like zeros. Okay, so if that's the case, I got more of my puzzle solved. Now I have this. Say again, Luke.
We already know that. I guess I can back that one.
So by finding the 0 right here, that was very, very important because that one allows us to know that part right there. We good? And now I know this relationship. If I plug in a 2, I get a 15. So I get this. I get this. Oh, sorry. Go back. Times 2. Okay. Help me out on this one. Okay.
Wait, why
Minus
is it
16.
9? 4 minus 16 plus negative 2. I don't know if that's right.
That's a 4, is that right? Yeah, that's
4 minus
8,
16.
16. So
Negative
15.
9.
I think
Wait. No, 4 minus 16 negative 12 plus 9. I was right. Let's try to trust myself.
2c plus 9, is that right?
What about it?
Okay. 9 and 4 make 13. Are we okay with a minus 9 here? Oh, cool. Okay, I finally got my answer, right? My answer, the original function is x squared minus. Go ahead, Noah.
What is it given the 9 and
Yeah, we're given that condition. We're given 2 conditions for the original function. One had a 0 inside it, so that helped out. Plus 9x plus 9. Okay, so we've got to one single function, is that right? Not a multiple of functions, right? Because we knew the initial conditions. That was the important part. So, no, that is it. All right. Yeah, because we took, there's our first derivative right here. And then we took another derivative. Okay, we good? Boom. So class real quick here. I know we have like 1 month left, right? But the second part, the integral part of calculus goes really quick. There's only 4 sections and 4 sections and we're done, basically. Yeah, and by the time we end, we actually are technically like if you go to Cal Poly, we would be done with a quarter and a third of another quarter. Yeah. So we'll be done. So I am going to do this here. I am going to probably do. I'm not going to take time during class time to do homework unless we have extra days. I'm going to pretty much just lecture on the days we're here. If you have homework questions, I'll take them down. I'll probably do a video of those homework questions just so we can finish up in time and have enough time to do stuff. All right. With that, I'll see you guys on Friday. Oh yeah, and then I'll send out a homework sheet